Okay, we have section 10.2, question P15, and we're asked to basically conduct a simple t-test here where we're given the values of a thermostat and we're going to compare it to some hypothesized mean, basically. So this would be the null hypothesis, is that the mean temperature is 72 degrees Fahrenheit, and then if we reject that null, we're going to assume that our thermostat is not working completely correctly. So we just type these values into Excel is one way to do this. Calculating the sample mean then would just be the average of these. Sample standard deviation. Notice that we have two different ones we can use, the sample or the population standard deviation. Here we're using the sample to, you'll know it by the fact that it's represented by an S, not a sigma. Sigma would represent population. The lowercase s is the sample standard deviation. Okay, how do we get our t-stat? Well, this is basically saying how far off from the hypothesized mean are we? So we got a 70.2 average. We're going to subtract out that 72, which is the hypothesized mean. And really, that would give us the difference between our mean and our hypothesized mean. But we need that standardized. We need it in a way that we can compare across different types of units. And so we divide out by the standard error, which is standard deviation divided by square root of the sample size, S over square root of n. And that gives us a t-stat. Now we just need to figure out what does that actually correspond with in a t-distribution with 6 degrees of freedom. So in a simple t-test, our degrees of freedom is the number in our sample minus 1. So that would give us 6 degrees of freedom here. So we go for the p-value. To do that, we're going to use the t-distribution. And notice we do have the chance to use two-tail. We do want to use that here because we don't know whether our thermostat is off to the above this 72 or below the 72. So since we're leaving the door open for it being either way, we're using a two-tail distribution. Our x is our t-stat value, and a degrees of freedom again is 6. So we press this and we get a numerical error. What's going on here? Well, the p-value is calculating all the way through to our test statistic. However, it's based on this being a positive number. So what we can do is do the absolute value of a test. Of course, you could just type in the positive version of that if you don't want to reference a cell. And I did abs, looking for absolute, ABS. This should work. Okay. And that gives us a p-value of 0.078, which is the answer. So what does that mean? That means only in, if the thermostat really is working correctly, so on average the mean is 72, if we were to take 7 random readings and calculate the sample mean, only about 7% of the time would we get something this far off from 72 or further. So I know that's a lot to comprehend. The p-value is a tricky, practically speaking, what we look at is this lower than whatever our cutoff alpha level is, which is usually 0.05 if you don't see anything otherwise. So 0.07 would not be below 0.05, so we wouldn't really have good evidence to reject the null. In other words, we don't have good evidence that the thermostat is broken. However, as we'll get into a little bit later here, this chapter, what really could be happening is our sample size isn't large enough to pick up the significant difference. And my hunch is that that's what the case is here. So if we had more data points, it's very possible our standard sample standard deviation here could be smaller because we're dividing by the square root of n, and then that would make our t statistic larger, and this right here would be smaller, so it would be below 0.05. But that's just a hunch. With this data here, all we can say is no, we do not reject the null with this p-value.